So today I'll be presenting the paper Im2Hands, Learning Attentive Implicit Presentation of Interacting Two-Hand Shapes. Well, as the title suggests, key contribution of this paper is it takes a single RGB image of an interacting hand, and from it generates an implicit geometric representation of those interacting hands. So if you're not familiar with implicit representation, well, take for example, something like a mesh would be sort of an explicit geometric representation because it has the level of detail or the resolution of a mesh of sort. It's determined by the number of vertices it has. And but in case of implicit, we do not have such something explicit like a vertices. So we have typically a neural net, and whichever you feed as an input into the net, a 3D coordinate of in pose space, and if there is any object in that particular 3D coordinate, the network returns a value between some sort of probability of whether that space is occupied by the object. So let's say at a particular point, if you're interested in getting a high frequency detail, that would not have been possible with meshes, since you cannot just increase the number of vertices. But in case of implicit representation, at a particular point, if you want a higher detail, you can just, as a query, you can use a lot of maybe 3D point inputs at that particular position. So in a way, implicit representations are, could be said, resolution free. So here's the overview. So we have an occupancy network, like I said, and we will be modeling a 3D scene. So let's say we model the scene in a 3D space. So a 3D point in that space would be the query in this network, and that would be conditioned on these alpha and beta. So alpha would be the shape parameter of the interacting hands, and beta would be the pose parameter. And then this network would put out two values between 0 and 1, one for the left hand and another for the right hand. So while the idea is to have this occupancy value be conditioned on alpha and beta, but these are represented as the image. And these are represented as the image as well as the key points of the hand. So as you can see, the key point has been represented here as a 42/3 matrix. So the 42 here stands for 21 key points, or sort of 21 key points in a single hand. If you're not sure about the kinematic tree, that would be something like this. For every finger, we have 4 joints, 4 key points, and in between, so 2 of the adjacent key points sort of make up a particular bone. And then we have another key point at the bottom of the palm here I think called the root key point. So in total, we have 21 key points per hand, and together we have 42. So what this paper does is shown its speciality is getting an implicit representation for 2 interacting hands. So one might assume, one could think like, why not simply use previous approaches that are already there for single hands? So Halo would be one such network here that sort of does this. It takes 3D key points as an input of one single hand, and it outputs the occupancy value and creates implicit representation of the hand. But the problem with that would be that models like Halo that de are dependent solely on the sort of uh, bone length features of the hand. So in such kind of models, soft tissue deformations that occur because of two interacting hands are not well represented, which is why we need something like a network like this paper has presented for two-hand cases. So here's a very brief background on Halo. Let's say, so let's call the network H, and you feed in as an input query, which is conditioned on the, let's say, conditioned on the joints of the hands. And then we have here this TB, which would be the bones transformation matrix. So what a bone transformation matrix is let's say here we represent this scene, like I said, in a 3D coordinate system, in a 3D space. And in that space, both the hands are there in a deformed manner, in, interacting with each other in some particular pose. So something like a canonical space would be like this, which is a 3D space, but it sort of has a fixed pose and a fixed shape. Sorry, not fixed shape. It only has a fixed pose. So what a bone transformation matrix would do is when you take a query from a pose space, which would be the space where the hands are, could be in any position really, in any pose. If you take a 3D point from there, and you transform it using the bone transformation matrix, that would map that particular point to the bone space in this canonical space. So for every single bone, we have a bone transformation matrix. And that bone transformation matrix is like, it's possible to calculate with sort of all the available information that we have at hand. And if you want more detail on it, you can look into the Halo paper on how to construct this bone transformation matrix. So what they are doing here is, for a query point, we transform it to a particular bone space, and for every single bone, we multiply that 3D coordinate with the bone transformation matrix meant for every single bone. And as well as, besides the canonicalized query point, represented by this TB multiplied by X, we also take as an input the bone length shape feature and the bone pose feature, which would be this f of omega. So the bone shape feature is derived from an MLP. Whereas the bone pose feature is derived from also an MLP, but that MLP takes as an input the transformation matrices for every single bone. So together, these features and the canonicalized query, you fit it into the H bar network meant for a particular bone, and you do this. The same query point is fed into a network meant for every single bone in the hand, and after the network gives out, let's say, some occupancy values between 0 to 1 for every single bone space, you pick the one which has the maximum value, and you take that point basically to be whichever bone network would give the highest output. You assume that canonical that the 3D point is supposed or sort of belongs to that bone space. So even in this network, the initial hand occupancy estimation is done using the architecture, which is very similar to Halo, except that it takes as an input another feature besides the inputs mentioned in Halo, which would be this f of x phi. And we'll look into how this is calculated. So f of x can be expressed like this, which is multi-headed self-attention between positional encoding of the query point x and the image encoding I. And this positional encoding is an MLP that performs positional embedding to map the input query coordinate x to a query feature vector of dimension d. And the image encoder vector is a standard image encoder in Vision transformer, which maps the input image I into p number of d-dimensional patches. And then this multi-headed self-attention sort of tries to figure out which patch this query point is closely associated to. So that's how, now we have this feature, and we have the usual features that goes with Halo, and we have the initial hand occupancy estimation. So they do this, so we have two hands here. They use this same shared network for both hands. So that's what they use for the initial estimation. But then in the later part, they refine it with the refinement network. So far we have come here. Let's say Halo takes 3D key points as an input and performs canonicalized query and sort of gives the occupancy output in canonical space. And so next we are going to cover the refinement network. So the initial occupancy estimation that we derive from this Halo-like architecture, we use those two here and refine them. We also need the input image here as well. The idea is to basically, for this network, to enhance the soft tissue deformation. And the main supervision for this is sort of associated to the image, RGB image itself. So which is why we need this input image besides just the geometric representation from Halo. So to do this, first represent the two hands as point clouds PL and PR for left and right hands. Let's say they have in total, let's say each of the hands are represented with n number of points in a cloud point, which are sets of isosurface points of each side of hand geometry. So what this implies is these n number of points in that cloud point are supposed to be sort of nearby the surface of the hand, either inside the surface or right outside the surface. These points are obtained by collecting 512 farthest points among the query coordinates evaluated to be on surface by the initial hand occupancy network. So what counts as a surface could be like, so occupancy value of 0.5 could be thought of as somewhat closer to the surface of the hand. And you limit the search between somewhat further and closer to the points that return 0.5. So after we have this 512 point cloud point representation, we now use that as an input to this cloud point cloud encoder. And this point cloud encoder takes as an input, like this, the point cloud representation, the image, and it returns a global latent vector and a local latent, and some set of local latent vectors anchored in 3D space. So for one particular hand, we so for one particular hand, we only have one global latent vector in a particular frame. All the sort of all the points in the cloud are given the same global latent vector, and this AS parameter is different for every individual point in the cloud. And the dimension of this AS would be m times 3 plus a for m number of anchor points. So m would be a sort of subset. This m is supposed to be sort of smaller than the n, the total number of points in the cloud point. So within point cloud encoder, the first input point cloud is pre-processed into this feature cloud with dimension n times 3 plus f. So what's basically happening here is this is this is obtained by projecting a point P in the point cloud onto all channels of the feature map G generated from a simple encoder-decoder CNN. So to clarify a bit more, let's say we have the subset of points. Then what happens next is this RGB image is fed into an image encoder-decoder architecture, and then it returns F channel of 2D feature maps. So the query feature are the a query point selected from the point cloud would then have to be projected onto a particular 2D map in this F channel feature representation. And whichever point in the 2D map it falls onto, you take that same point across all the F channels and get a feature vector out of it. And you do this for every single point in the cloud point representation. So that's how you have the this FS. Then feed the feature cloud to encoder of AirNet to get global and locally anchored point cloud features. So this AirNet is another architecture that you would have to go to the paper to find more about. And then next comes the context encoder using so these features that we obtain as well as this feature. We extract a latent code that encodes interacting two-hand shapes and image context as follows. So the context encoder takes as an input the Z, sort of the latent vectors, global latent vectors for both the left and right hands. And then there is a latent vector for the image I as well. So this context encoder is also an MLP that extracts the context feature, and this latent vector for the image is just the global bottleneck feature from the image encoder decoder previously used to extract G. So this latent image vector would be this vector right over here in between the encoder within the encoder decoder architecture. So yeah, once we have this context encoding, we then move on to the sort of point cloud decoder, which takes as an input the query point and this context encoding that we just generated, and this AS from the refinement module, and the initial occupancy output from the Halo-like architecture. So all of these are used in the decoder. And the decoder is also just the architecture of it is similar to the decoder of AirNet. So now we finally have the overall occupancy value for a particular query point. But in case, let's say, this whole architecture needs the image as well as the sort of, since Halo relies on 3D key points. We also need the 3D key points, but let's say we don't have the 3D key point in a data set. We can also use an off-the-shelf, any off-the-shelf three key point predictors. So that, which is why they also introduced the key point refinement module as well. So the key point refinement could be represented like this in the equation above. First, extract the input key point features using the key point encoder, which takes as an input the index and the coordinate of each key point in a shared MLP, so which would be this thing. And then a two-hand skeleton graph is built with the initial node feature set as the features extracted from the previous key point encoder function. Then after you have this two-hand skeleton graph, just feed it to any graph convolutional network and then perform again multi-headed self-attention with the output of the graph convolutional network and the image encoding of the RGB image to get the final key point values, sort of refined key point values. And here's how we calculate the losses in here. For the initial hand occupancy network, they just use the MSE loss. And for the two-hand occupancy refinement network, they use penetration loss as well, besides just MSE loss. So penetration loss would be, so this RL and RR would be present if the output for these occupancy refinement network is above 0.5 for both the left and right hand. So that would imply that the model predicts that at a particular query point, both hands are occupying a space with a probability of more than half. The penetration loss is intended to penalize that. And the input key point refinement network is also just trained by an MSE loss using the ground truth and predicted two-hand key points. For the experiments, they mainly just use the Im2Hands 2.6M dataset, but for qualitative evaluation, they also use two other datasets as well. And this is really the main result there is. They compare with other existing methods. While Halo is only meant for a single hand, for just joints and single hand, they modified it to be compatible with both hands and also take image encoding as an input. Well, in the end, yeah, as you can see, this paper comes out to be the top in all the metrics. And here are some qualitative results. And they have highlighted the points where the other previous methods tend to fail. Like even though in the input image, there is clear contact between the two hands, Halo and Im2Hands, which are mostly pretty much modified, which were originally meant for just a single hand representation, sort of failed to capture this, but Im2Hands captures it pretty well. So that's it from me. Thanks for listening.